Yeah, yeah. Well, actually,
Okay.
I tested earlier.
Now it works.
Yeah, yeah. It just needs to have that green light flashing occasionally.
Green light. Yeah.
We're waiting for this.
I see students here.
Yeah.
Oh.
Johnny said that everybody, all students who came got an A.
That's a method. It's a good one. In Wednesday, they do exactly that. No pressure. Доповідь буде дадена по-українськи.
А вже ж.
Anyway, so maybe we have a quorum. It's a wonderful pleasure to invite Boris Tsygen from Northwestern University is going to speak on microlocal invariants of symplectic.
Thank you very much. It's a great pleasure to be here. So I will, first of all, real brief, let me, well, I will very briefly remind what is a symplectic manifold, what is a Lagrangian submanifold, what is a Hamiltonian flow, and then address somehow, not even kind of with this question in mind, with this phenomenon in mind that often, if you have a Lagrangian submanifold, you cannot displace it from itself by a Hamiltonian flow. And with this in mind, I'm not even sure how to say it, well, things or maybe objects I will discuss several situations where you start with something well meaningful and produce
well, what's it?
pardon?
What's
No,
F?
it's just a,
F, objects, or objects of various types. Could be, I don't know, well, sheaves, modules, maybe Lagrangians themselves. Maybe, yeah, not Fourier integral, but generalized functions with distributions, yeah. And then, yeah, so maybe I should say that not always, but often, microsupport of a thing will be Lagrangian. And so with that in mind, I will in any case, even not with that in mind, so this is a way of starting. I will construct an invariant of this symplectic manifold, which is not a number, it's rather a category. And well, it's an invariant. It distinguishes between manifolds and so on. But in particular, it is inspired by, using this category, one can study those questions. So real quick, maybe let me, again, there was some sort of a pre-talk in the at noon, but well, in any case, this is the definition of a symplectic manifold. A symplectic manifold is a smooth manifold with a differential to real to form, which is closed and whose end power is a non-degenerate top form. And so at any point and in some local coordinates, which are called Darboux coordinates, I subdivide them, my coordinates, into two groups, Xi and X, and this is the standard form. Also, maybe Lagrangian submanifolds let me just say that it's an n-dimensional smooth submanifold, which in some Darboux coordinates it is given by those, by this formula. Okay, then
You can move.
pardon?
The frames are movable, so if you want to keep some of your space, you can move it to the right.
Yeah, thanks. Poisson bracket. Again, just let me say that in any Darboux coordinates, it's given by this formula. It's actually a Lie algebra structure on functions. And finally, Hamiltonian flow. What does it mean? It means that So it's a one parameter family of diffeomorphisms, transformations of M, which if you apply to function and differentiate, you get a Poisson bracket with some fixed function, and this function may depend on T. It's a non-autonomous test. So in particular, automatically, it preserves the symplectic form. Also, if you apply it to functions, it's an automorphism with respect to Poisson bracket. Okay, so and again, maybe I said more at the pre-talk, but I want to make this definitely, you know, self-contained, this talk. But again, maybe let me just say that we have one could say a lot more with respect to this question, but just let me say that we are dealing with something like this in mind. So maybe let me just say that however important Lagrangian submanifolds are, they usually will come from something. So they arise from some objects like sheaves or modules or distributions, or one could start with a Lagrangian submanifold. So let's keep that in mind, and let me tell you what I'm going to kind of, what problem, so to speak, maybe among others, I am going to discuss. So starting from a symplectic manifold, I want to construct a category, and again, a category with an asterisk because it will, well, it will keep some axioms and maybe not some others, or some others will be relaxed. So, but at least when you have a category, you must have some objects, which I will denote somehow in my mind. Just the shift theoretical language is kind of closer, so I will denote them by FG, etc. For every two objects, I will want a morphism, and complex of morphisms, I would say. Again, there is an asterisk because sometimes it may be, if you relax your conditions a little bit, it may be not a graded complex, it may be a Z2 graded complex or something. Well, there should be, again, composition, which is a morphism of complexes, subject to some maybe relaxed, maybe not relaxed associativity conditions. Okay, also maybe it's an important feature that they will be over a bigger ring of scalars, which, well, the Novikov ring is one way to say it. Sometimes you don't need it. I will describe later what K is. And so it will be built into the theory that for every object, I can construct a closed subset, which is often a Lagrangian, often maybe something else, sometimes singular, but in very interesting cases, it will be non-singular. Okay, and then if you have two objects and their microsupports are compact, then the complex is acyclic, it has no cohomology. And finally, assume that we have a Hamiltonian isotopy which is, let me say, identity outside the compact, for example. Well, it's rather crucial, but one can tinker with it. And then one can, actually, one defines a functor on this category. Let me just do it on objects. First of all, microsupport is well behaved or correctly behaved. It just, and the complex or the cohomology of the complex does not change. So once again, it may be a bit technical, but basically to an object, you associate microsupport inside them. If microsupports do not intersect under some condition, the complex of morphisms is 0 if and also Hamiltonian isotopies act on everything, preserving. And then, so if you have this package, then in particular, maybe you have that.
The complex is 0 or acyclic?
Equivalent to 0, acyclic, yeah. And then having that, as soon as you establish that 1 is not equal to 0 in the self-endomorphisms, then you know that the microsupport cannot be displaced by any. Okay, often you know actually if in good cases when L is a Lagrangian smooth microsupport of F, then this will rather be cohomology of L of the Lagrangian submanifold. So you will get quite a few intersection points. Okay, so this is sort of the program or the outline. Any questions so far?
So morphism would be a complex between two objects.
For any two objects, you will define a complex.
Yeah, that would be the morphism.
That will be the complex of morphisms. Yes, so it's rather a differential graded, well, as they say, category enriched in complexes or differential graded category. It may be a infinity category, which is a relaxed, condition.
Sure. So there are complex there in the last corner. Let's say you don't need a phi star F or.
Yeah, that if I replace my object F, so somehow the previous thing says that I can act on F by Hamiltonian isotopies.
Mm-hmm.
And the claim is, the property that I want to have is that if I do that and then consider this complex or this complex, well, the cohomology does not change, at least. Well, one can say more. But.
Yeah, it's just actually in the second.
Is this isomorphism is on the cohomology level, or is there information on the complex level?
It will be actually, well, a zigzag of, I am not saying that there is a map of complexes, there is map from something third here and here. Both of them are isomorphisms on cohomology.
Okay, and also like when you change F and G, do complexes will still same or like will be same?
Oh, no, they're very, I guess in every case they're very different.
Okay.
And what would be the composition of morphisms? Like just tensor product or?
Well, it's one has to define. Those are again. This is the complex of morphisms. Yeah, this is the complex of morphisms F1 to F2, and well, one have to. Well, it's part of the structure. One has to define it somewhere.
Yeah. So it's usual morphism in your sheaves of modules.
Well, if your sheaves of modules, it's kind of at least it's variation on. It's a variation on the theme of usual morphisms, yeah. For Fukaya category, well, it comes from counting holomorphic disks.
Can you say more about micro support?
Yeah, I'm coming.
Yeah.
What does non-displaceable mean? Means you cannot shift it off itself using isotopy?
Yeah. At least maybe well in a non-compact using Hamiltonian isotopy, which is identity outside of a compact. You will prove the catalyst invariant somehow. Well, at least, you know, under symplectomorphism, you get equivalence category. That's your transformation. Yeah. So first of all, very briefly, let me just say that Fukaya, just his objects are Lagrangians themselves, maybe with some extra structure. And I think you will see what that at least some extra structure is needed. And so and of course, well, micro support of it is then just, well, one can say that micro support of L plus this extra structure is, of course, just L. Okay, and then and here we have, of course, or well, they have quite some difficulty. They require that L1 intersects L2 transversally. And oh boy, and I forgot to say what K is, but well, I will do it later. And then the complex is by definition just, you know, as many as many copies of my ground ring K, which I haven't defined, as many fixed points you have. And then the differential as well as composition as well as something else, higher composition. Well, let me just say that it involves disks or holomorphic disks and very beautiful nonlinear PGE, so coming from Gromov, Hofer, Floer. So it's a beautiful theory, and I guess, at least so far, maybe I will say nothing about it. So let me try explore other, arise from some objects. So let me. And let me give a kind of motivating example, which won't go anywhere, because I don't know if it would be maybe interesting, but I don't know how to say it. But First of all, if you have a distribution on a manifold X, it has a wavefront, which is again often Lagrangian, closed, conical submanifold of T star X. And maybe, well, let me say a word because so given a distribution, what you do, denote it by U, yeah? Let me really say one word, unfortunately. So at a point X of my manifold, what covectors are singular to it? So what you do, you first kill it outside and then take Fourier. So it will be now a function in the dual variable in Xi. And and then consider those directions in Xi in which the resulting Fourier transform is not rapidly decaying. And those are, well, singular codirections for a distribution. So declare it to be, I think maybe the correct notion is wavefront of the distribution.
What means direction?
Co-directions, yeah, well, directions, I mean, yeah, so one feature of it is let me give you an example. Delta function. So of course, its Fourier transform is just some constant times identity of Xi. So yeah, so if I draw a plane X and Xi, then it doesn't, yeah, by the way, you see from the definition, it if it has a non-zero Xi, then the entire direction, the entire ray is there also, so it's conical. And here as well. So here it is, wavefront of the delta function is just okay, and then one can try to play with heaviside functions, and you will get half ray, I mean full rays, but in one direction, and so it would be beautiful, I think, and yeah, I talked, I remember, to Polterovich about it. He also is kind of wondering, it would be beautiful to have, you know, some category based on that, but I have no idea. Okay, but I think this, especially when it comes to heaviside functions, it already brings some motivation. So with this in mind, sheaves on X. So let me recall that. Let's say, I don't know, K module, K is our, I mean, whatever, Z2, Z, R, C. So a sheaf on a manifold assigns to any open submanifold an abelian group, whatever, a module. And you can restrict to smaller open subsets. And of course, if you do it 2 times, it's consistent. This will be a pre-sheaf, and then there is some gluing condition that again, maybe having delta functions and heaviside functions in mind, why wouldn't I? So first of all, so maybe, well, okay, this is the first example, and maybe let me just draw what I mean. If I have my U here or here or here, so call it V, all of them, let's call V. Then I assign to it a one-dimensional K module. As soon as I, well, at least partially leave my thing, so we'll call it I have 0. Okay, so it must be, it indicates, well, again, one has to, what happens if you have 2 connected components here or here? Of course, you associate to it 1K and not 2, but this is the idea. Okay, so this is one example. This is
U is the circle. This.
No, I am sorry. My U is open. It's sorry. It's an open subset. How about a closed subset? So if this is my closed subset, it's a little bit different. Again, if it's inside or has not completely left my z. So for those v, kz of v is k. And if I am outside is 0. Maybe I am saying something stupid, but at least when everything is nice, you know, when you don't have some, yeah, I wouldn't swear for some badly behaved closed subset, but if they are as drawn, then this is the correct definition. Okay, those are two examples, and of course there are many others. Yeah, for example, how about, well, we will see examples.
This is generated from microlocal structure.
Yeah. So Kashivara and Shapira, they developed this microlocal theory of sheaves, and so for every sheaf, they describe the singular support. Maybe let me spend a few minutes. So first of all, x is equal to r. So how about we start with examples? Singular support of the delta sheaf will happen to be the same as singular support of the delta, as the wavefront of the delta function. Singular support of this thing will be, let's see, I hope that I get it right. Hopefully, I mean, definitely you will have two rays. First of all, of course, you will have this ray and let's see. And I think you have this. And so on. And maybe, how about if I have an open, half line, then the singular support will be like this. Why is that? Well, I haven't given a definition, but the definition goes like this. So maybe let me consider the idea of a definition. Let me draw this, should I say, cigar, you know, where the mouth is here, so to speak, and the ashes, the fire is here. So, and let me again kind of, well, it's sort of thickened direction, yeah? I'm saying that this I am saying that this direction is singular for F. Why is it singular for f? Because when I kind of make it an open set like this, yeah, and when I evaluate f on this entire open set, it's not the same when I restrict it just to the front part with the ashes and the fire. It's not the same, yeah, because my delta is inside. So this is k, and this is 0. So when I am moving away in this sort of thickened direction, and then just localize myself here, throwing away this, the result changes. And similarly, of course, here is a singular direction. So all directions are singular. At 0, therefore, I must include both codirections. How to say it better? More generally, maybe it's more instructive on in two variables, or more than two, but let's say two. So you have a plane. Once again, there are no xi's, nothing. There is just x1 and x2. And let's say that you have this, let's say it's smooth, a smooth hypersurface, and half of it, and the sheaf is concentrated there. So what do you do? Maybe let me draw a few non-singular directions. So those again, intuitively, I am not given exactly a rigorous definition, but when I move in those directions, nothing happens to the sheaf, yeah, because so if this is, let's say, U, and this is V, F of U and F of V are the same, they are K. Yeah, my sheaf is here, and both are K. Now, let's say those are very much singular directions when I consider this open subset and then restrict my sheaf from here to here. On the big thing, I get non-zero. On the small thing, I get 0. So those are singular directions. Okay, finally, how do I define singular support? Well, the definition is, and it's almost the kind of 80% or 95% of the correct definition, is
What about the tangential directions to the boundary? Are they singular?
No, well, I would say they are non-singular, but they are maybe. Let me tell you this: when is so to be a singular covector, all negative, and this kind of well mitigates the question about the boundary. All negative directions with respect to psi must be singular. And when you look at this picture, you see that the only psi negative directions, the only way to have this is to launch it perpendicularly. If you launch it kind of like this, then there will be some singular and some non-singular directions. So this is, of course, an illustration of this. This reminds me of, actually, it was precisely about this very, very prominent.
So this zeta is in 4-dimensional space here. Your x is a 2-dimensional thing here.
Yeah.
Zeta is a 4-dimensional
Yes,
vector.
it will be in 4-dimensional vector space.
And we only see 2-dimensional
You only,
when you see the direction.
yeah. It will be maybe, yeah, let me write it once. I mean, if it's a smooth curve, yeah, it will be either there is a strict inequality, you are in kind of in a smooth, it's the same as constant shift, yeah, if you are here, or you are on the boundary, and then there is only one ray that is allowed, and is the gradient of f, the differential.
What you draw there is x1, x2. When you draw direction, it's only x1, x2. So zeta 1, zeta 2 is.
Pardon?
So when you draw a singular direction on the
Yeah.
picture, that is actually x1, x2. In your definition.
All this picture is in the plane x1, x2. And on this picture, I am drawing the only single on the boundary. I am drawing the only cotangent vector. I am drawing it just on this picture because I don't have any other room, but it's a covector, you know, it's a tangent covector to this plane, which I somehow draw on this plane again. And again, it's singular for a sheaf if all its negative, you know, if its negative directions are singular for the sheaf. And this is an invariant thing. Yeah, so by the way, there is a big restriction to that because, for example, you cannot, you often or typically get Lagrangian submanifolds, but you cannot get anything non-singular, for example, because they are all conical. They are all kind of something like this. But, yeah, so here comes Dima Markin's idea that you can they will be not all sheaves, they will be sheaves with a property. And the property is that they are kind of forward-looking in the direction t. So let me give a typical example. So given a function on x, a real valued function, my sheaf is I think. Correct. So if this is my t, and this is my x, then it will be, so a typical this is the closed subset on which I am allowed to consider my sheaf. So again, I guess the key word is that it's forward-looking with respect to t. So maybe, well, let me try to finish. So I am basically, yeah, so we can take a typical home, as was mentioned before. But actually, another beautiful observation of Dima is that there is an enhanced home namely, which makes it a K module, and K, I haven't defined K, so let me, in the remaining minute, define K, and then claim or state Dima's theorem, that Dima-Tamarkin's theorem, that there is, well, it satisfies all this package. K is the Novikov ring. It is so T is a sort of formal parameter. Those are my numbers, whatever I have. And Cj are actually real numbers, and moreover, that they go to infinity when j goes to infinity. So that's it. And so again, Dima-Tamarkin's theorem is that for T star x, it does the trick. It gives you this package of 6 or 7 properties. It's for T star x. How to glue it together? Again, Dima-Tamarkin has some versions, but I mean, well, I'm not sure that at the moment anybody knows what's going on and how to glue. But also, there is an alternative approach that is kind of more distribution inspired, which seems to give conjecturally there is also this package, and there is some connection, some functors between that picture and Dima's picture. And well, it works for a general symplectic manifold with some restrictions. Okay, thank you very much.
What's the name you frequently talk about?
So is it clear how one goes from the sheaf setup to defining microlocal structures for just even T star effects?
Well, I mean, first of all, this sheaf setup, you can call that a microlocal structure, but maybe more traditional microlocal is. Huh?
If you have something like
On the
wave
potential.
one set and stuff with direction, is microlocal time?
Yeah, but if you want something more traditional microlocally inspired, like again, very extremely roughly speaking, you know, just maybe. So if you have a distribution that I was talking about, maybe somehow age dependent, where age is a parameter, you associate to it, you start acting on it by, let's say, differential operators. Again, maybe by age differential operators, which are by definition, I don't know, locally. Your differential operators are, your derivations are multiplied by age. you start acting on it. You will get new distributions, and obviously you will get a modulo over this ring. So in itself, this such from that you can pass to a sort of support, basically just setting h equal to 0, you can pass to some support. But it's tantalizing and interesting, but that's not enough. And basically one idea is that you also you also allow to act on it by Fourier integral operators, again, somehow cleverly, you know, depending on h. And you get a module over a bigger thing. And that has more adequate properties, and one can formalize it. And at least there is a proto-functor, probably a well-defined functor on the cotangent bundle from this picture to the sheaf picture. So not vice versa, I am not sure. But from this kind of, not true my microlocal, but kind of more classical microlocal to the sheaf picture.
But what is the material from symplectic to contact or something by adding the direction?
The contact structure plays a role, but I mean, definitely that there is some contact geometry in it.
Any other questions?
I mean, maybe this question is nonsense, but when you define the wavefronts and when you are calculating for on the real line for the origin, you get this wavefront on the on that direction, and also in the singular support of some other thing, you get the same thing. Is there any relation between those wavefronts and the singular supports of some certain sets? Singular supports of some certain types of distribution?
Between sheaves and distributions, yeah, more than an analogy. Yeah. I don't know. Yeah, I mean, I guess I just don't know. I'm going to Japan. I will try to ask somebody, but.
Okay, thank you, speaker.
Let me, if you excuse, I kept and I forgot. So I remember trying to explain to this, you know, prominent European topologist, homotopy theorist, precise with this, you know, something like this. And he says, I refuse to know anything that you can explain to me on the straight line.
We're gonna have a dinner.